All right, folks, so first thing is congratulations. This is our last topic. We're going to look at bonding, and there are two parts to it. And we are going to start with the covalent bonding first, and then we're going to move on to ionic bonding. Now, it is very much dependent on what teacher you had for junior cycle as to the depth with which they may have gone into bonding, but I'm going to make the assumption that we all know nothing, and anything after that is an advantage. So I'm working off roughly page 142 of our yellow-orange book, and here is our periodic table, and we are going to do some coloring in. So when we talked about the periodic table way back in terms of our introduction, we said that if you find boron and you draw a little stairs down from it, so this is the little baby sitting their butts going down the stairs, that is the separation of our periodic table. And we separate the periodic table into metals and into non-metals. So you have better coloring skills than me, but I'm going to turn this side into blue, and I'm also going to choose hydrogen over here. So our blue are non-metals. And the reason why hydrogen is here, to remind you, is that because it has one electron in its outer shell, it fits in with the group 1 properties. You will see occasional periodic tables where hydrogen would be in the same line as helium, but it will be over here. And it's only because it's a non-metal, but it just doesn't fit any of the other groups. So we also then need a color for our metal part of our periodic table. So we're going to go orange for this. So you just pick two different colors, and we go with that. So these are our metals, and it is very clear that metals are way more abundant than non-metals. So as a general introduction, ionic bonds form between metals and non-metals. So when you look at the formula of a compound, if you can get your hands on your periodic table and you look, and if it has something in the orange section, something in the blue section, then it's an ionic bond. Whereas covalent bonds will form between non-metals only. So it's only things that live in this blue section. Now, you are going to have to be able to draw covalent bonds for the SEC. So there are some things that you need to remember when you're doing it. You may have, when you did junior cycle, have a definition for a covalent bond, and that definition still applies. It hasn't changed. We've dealt with this now, what type of elements covalently bonded. That has been done for us. And our definition is when one or more pairs of electrons are shared between atoms. That is the definition for a covalent bond. Now, as we move through this, we will start putting the words polar and non-polar in front of the word covalent bond. But if they ask you for just a covalent bond definition, boom, this is it. If we have to do polar and non-polar, we slightly vary some of the language that we add to this. Now, on the bottom of page 142, I'm going to deal with that in a second. But before we go there, I would just like to show you this. So, what the hell are covalent bonds? What does it mean if we're sharing electrons between atoms? So to do it, we're going to use hydrogen. So hydrogen is in our periodic table is a 1 and a 1. And when we look at hydrogen, what is the protons, electrons, and neutrons? What is it telling us? So hydrogen has one proton, one electron, no neutrons. And in terms of bonding, it is the electrons I'm interested in. So we're looking at our structure, and here it is. So the little lines are indicating attraction between my positive nucleus and my single electron. Okay, they're going to be attracted to each other. Now, hydrogen, because of where it lives on the periodic table, wants to essentially be helium. It wants a full outer energy level. That is happiness to it. How does it? So it's going to need, if you're hydrogen, one electron to get another electron for happiness. So when it comes across another element that has one electron that it can give it, they will be attracted to each other. So we've already done our atomic radius idea that there's no screening here. So my little electron is very much attracted to the positive nucleus, but it will also be attracted to a positive nucleus in a different element. And when they get close enough, they will actually share their electrons, and we've now formed this idea of a covalent bond. So we've gone from hydrogen atoms to hydrogen molecules. So this little H2 puts it into the molecule range. And we've already had our definition of molecule way back. 2 or more atoms joined by a covalent bond. Okay. And we've had our definition. So this, if you've got one shared pair, it is a single covalent bond. We are actually going to talk in terms of using words called sigma and pi to describe our bonding. But one shared pair is where we're at. So we will draw hydrogen again. On page 143, you have a table of a whole load of compounds, and I'll show them to you in a second, and you have this diagram in there. Now, the good thing is we don't have to draw all of the internal stuff that's within the atom. We're only interested in the outer shell electrons. So at the bottom of page 142, you have a sentence. So row 1 has 2 electrons. Row 2 has 8 electrons. Row 3 technically has, and it says row 22 in your book, but it's only row 2. So row 3 technically has 8 electrons. So we're not talking energy levels now, we're just talking rows. And row 4, as far as we're concerned, has 18 electrons. Now, if we had to write an old school electron configuration, that would be 2, 8, 18 for argon. Okay, and we are, when we look at something like this, this is called methane, CH4. When we look at methane, what you are looking at first is we're looking at the carbon, and carbon is 12,6, and we've said we're only interested in the outer shell electrons, so we're only interested in electrons. So carbon, because of its atomic number, so again you can use 8-man if you want to do it. So 8-man is the atomic number, is equal to the number of protons, is equal to the number of electrons, and the man is mass minus atomic, so 12 take away 6 is equal to 6 neutrons. So this is protons, this is electrons, this is neutrons, and this is what I am interested in. So if you look at your periodic table again, this is a little bit like using SPDF's configuration. We now have 6 electrons for carbon, and they will be arranged in a 2-4 arrangement. Now, we have, if you live in row 2 and you have 4 electrons, you really want to look like neon. You want to have a full outer energy level, and it's actually easier for it to gain 4 than it is to lose 4. You got to trust me on this one. It's clearer on the other ones. So we have to find now 4 electrons for carbon for happiness, and each hydrogen has that 1 electron. So if we draw our before diagram and we go 1, 2, 3 and 4 in our before, and we now have hydrogens that have 1 electron each, and hydrogen, we've said, needs to have 2 electrons for happiness. Apologies. So these, what's going to happen is this is going to be attracted to this, this is going to be attracted to this, and vice versa. They're both going to be attracted to each other, and they will share these electrons with each other. And now if you look over here at this big one, we'll do it this. So this hydrogen has 2 electrons, this hydrogen has 2 electrons, this hydrogen has 2 electrons, and this hydrogen has 2 electrons. So hydrogen is happy as a pig in poop. It has a full outer energy level. Life is perfect. Whereas if we look at carbon and we count carbon's electrons now, 1, 2, 3, 4, 5, 6, 7, 8. Carbon is also happy because it now has a full outer shell. So we're doing a couple of things here. We're figuring out what is the number of electrons that we have. We're trying to figure out how many do we need to get a full outer shell. Am I giving them away or taking them away? So does carbon want to be neon or does it want to be helium? You're going to have to make a choice, and we'll talk about it as we go through it. And then we make sure that if it's hydrogen, it has 2 electrons in its outer shell, and if it's carbon, that it has to have 8 for happiness. That's, you know then that you've done it right. Now for most things, hydrogen is the only one that has 2. Everything else we'll be looking at, 8 is going to be our magic number. So these are all the different bonds that you have to draw. or the different molecules that you're going to have to draw, and I'm going to draw each and every one of them for you. So we're going to go into here and we're going to very quickly start with hydrogen. So hydrogen has, I'm going to draw you the little before picture. You can draw it, not draw it. It doesn't bother me in the least bit. We call these dot and cross diagrams because one is a dot, one is a cross. You could do them in both in dots as long as they're both different colors. And obviously this is going to be attracted and they're going to be attracted to each other. So our after picture is kind of like a Venn diagram. At least I draw it like a Venn diagram. So we have a dot and a cross, and we have a H and a H, and this is one shared pair of electrons. And its description, I'm going to give you its description and we'll come to it later. It is one sigma bond, it's called. And we'll talk about what that actually means. So we've done the CH4 already. So CH4 is called methane, and there are 4 sigma bonds in methane. I'm going to maybe change how I say this. I think we're going to say that each CH bond is equal to 1 sigma bond, and that will make sense, I promise, very shortly. Not this lesson, but the next one. Okay, so the next one I'm going to look at is F2. So F2 is fluorine. So we are going to have to draw 2 fluorine atoms, and we need to figure out how many electrons does fluorine have in total. So fluorine has electron configuration of 2 for the first row and 7 for the second row. So it's this 7 electrons in its outer shell. So when we draw it, we pair up our electrons because that makes it really easy to count. And we have one unpaired here, and I'm going to just change my color of pen, and we are going to go dot 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 dot. So I have 7 electrons. I need 1 to get that outer full energy level. So these guys are going to be attracted to each other. So when we redraw, we do our Venn diagram type scenario. We go XX, 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 1 here, and then we change our color. So now we're showing all the electrons, and there's only 2 that are involved in bonding. And if you do your count around this fluorine on the left, there is now 1, 2, 3, 4, 5, 6, 7, 8 electrons, happiness. If you look at this fluorine on the right, 1, 2, 3, 4, 5, 6, 7, 8 electrons, happiness. So again, in fluorine there is going to be 1 sigma bond in fluorine. So F2 is fluorine molecule, and it has 1 sigma bond because there is 1 shared pair of electrons. So 1 shared pair. And obviously each CH bond up here is a shared pair. So I'm going to just do a bit of erasing from the top. Let's see where we go. Now we are going to look at the CCl4. So CCl4 is called tetrachloromethane. Now you wouldn't be able to get that because methane is in an organic molecule and we haven't done organic chemistry yet, but we look at each one individually. So we're looking at outer shells. So carbon, we now know from earlier, it has an electron configuration of 2, 4. It requires 4 electrons in its outer shell for happiness. So here we have carbon. So it's got 4 electrons, and we need to find 4 more electrons now for carbon to have happiness. So chlorine has an electron configuration of 2, 8, 7. So each chlorine is going to have 7 electrons in its outer shell. So it only needs 1 for happiness. So chlorine is going to share 1 of its electrons with each chlorine is going to share 1 of its electrons with each carbon electron here. And that is how it is going to become happy. So we go dot 3, 4, 5, 6, and 7. We go dot 2, 3, 4, 5, 6, 7. We go dot 1, 2, 3, 4, 5, 6, 7. And I'm going to go white, and we say 2, 3, 4, 5, 6, 7. So if we just look at the carbon ones, so if you look at carbon now has 2, 4, 6, 8 electrons. It has a full outer energy level. It's ridiculously happy. And if we look at each chlorine, so go here, each chlorine now has 1, 2, 3, 4, 5, 6, 7, 8 in total. These have 8 in total. There is 8 in total here, and there is 8 in total here. So chlorine is now happy. So each CCl bond is one shared pair and one sigma bond. So we have done kind of the straightforward ones where it is relatively straightforward in terms of electron pairs. So we are going to get rid of this, and we are going to go on to the next two. And we are going to go for NH3. So NH3 is called ammonia. And we look at nitrogen. So we now know hydrogen is going to have, if we have to draw hydrogen by itself, it needs one more electron. So you may be able to work out now how many it's going to have to share with nitrogen. So nitrogen's electron configuration is 2, 5. So 2 in the first row and then 5 in the second row to get to nitrogen. So nitrogen's outside is going to have 5 electrons. This essentially wants to be neon, so it needs 3 electrons for happiness. And it's going to get those 3 by sharing with each hydrogen. Now I'm going to draw them down here like this, and so I'm putting in my hydrogen and I'm putting in my single electron from each hydrogen, and we now have 5 electrons for neon. So 1, 2, 3 get shared, so nitrogen has 2 left over, and we put them up at the top. Now we call them, when we put them up at the top, we call these guys are called lone pairs, because they're not involved in bonding, whereas these guys down here are called bonding pairs, and we'll come to that in a little while. Okay, so we very much draw the diagram this way because we're going to be adding to the information that we know about these dot and crosses of ammonia. So that is what ammonia looks like. I don't think there's anything else left to say. So the next one that we have is H2O. So that's relatively easy in terms of its name and its formula. So H2O is water. We know that hydrogen has 1 electron in its outer shell, so it's going to want to share. So in terms of oxygen, what do we know? Its electron configuration is 2, 6. So it has 6 electrons in its outer shell. It wants to look like neon, so it's going to require 2 electrons for that full outer energy level. So we draw our oxygen, and we now know it's going to bond to hydrogen, and I'm putting these down here at the bottom, and these are hydrogen's electrons, and we know it requires going to share 2 electrons, 1 with each hydrogen, so that's 2 of its 6. So this time we draw our other 2 pairs up here at the top. So this has 2 lone pairs, and we will get to that, and these are 2 bonding pairs down here. Now I suppose it didn't say it for the NH bonds, so I'm just going to put the little caveat. So each NH bond from our ammonia is again 1 shared pair and it was 1 sigma bond. And for water here, each OH is 1 shared pair of electrons, and it is 1 sigma bond also. So we have done everything thus far. The 6 that we've done all are sigma bonded. There's 1 shared pair involved. So now we up the ante and we start looking at things that have 2 shared pairs. So these are double bonded, and we describe them in terms of sigma. We use 2 words in a minute to describe them. So the first one we're going to look at is oxygen again. So we have said oxygen is 2,6. It has 6 electrons in its outer shell. It wants to be neon if you look across your periodic table, so it needs 2 electrons. And if you have 2 oxygens and each oxygen needs 2 electrons, well then each oxygen is actually going to share 2 of its electrons with the other oxygen. So 1, 2, 3, 4, 5, 6 for 1 oxygen, happiness. The other oxygen now I'm going to do as dots. So 1, 2, 3, 4, 5, 6 for my other oxygen. So if I count across or look here, so 1, 2, 3, 4, 5, 6, 7, 8, this oxygen is happy. If I look over here, 1, 2, 3, 4, 5, 6, 7, 8, this oxygen is happy. So here now the oxygen-oxygen bond. So each oxygen, so sometimes they can draw it like this, with the little equals being a shared pair. So each oxygen is 2 shared pairs of electrons, but it is, in terms of describing the bonding, it is 1 sigma bond and 1 pi bond. So we'll come to this language again at a later date. So that is oxygen, a molecule of oxygen. So the next one is then carbon dioxide, CO2 carbon dioxide. So we're now just using the information we have about carbon, and we are using the information we have about oxygen. So we start with our carbon, and we've said carbon is a 2,4, it wants 4 electrons. Oxygen is a 2,6, and it wants 2 electrons. And essentially both of these want to be neon. They want that full outer energy level. So how are they going to do it? So because our formula is CO2, then that must mean that carbon is going to share 2 electrons with 1 oxygen and another 2 electrons with the other oxygens. So this is my carbon. We draw kind of a Venn diagram, and we say this is carbon's electrons, 1, 2, 3, 4. Oxygen has 6 outer electrons, so we put our O in our O, and oxygen is going for 6, so we are going to go 1, 2, no, I'm going to change how I do that. I'm going to put them up here, 1, 2, 3, 4, and to get 8 it needs to share 2. So now that has 8, and then we are going to go for my other oxygen, and it has to share 2, and 3, 4, 5, and 6. So again, if we look down at count around, so for carbon, 1, 2, 3, 4, 5, 6, 7, 8, carbon is now happy. For this left hand side oxygen, 1, 2, 3, 4, 5, 6, 7, 8, it is now happy. And our last one is going to be this right hand oxygen, 1, 2, 3, 4, 5, 6, 7, 8. Happiness is upon it. So our description for this, so each carbon oxygen bond is 2 shared pairs of electrons, and the description again, if you're sharing 2 pairs, is there's 1 sigma bond and there is 1 pi bond in there. So we flip over our page and we do our last one, which is something that is triple bonded. So triple bond means 3 shared pairs of electrons. We have already looked at nitrogen. So our nitrogen is a 2-7 electron configuration, 2 in the first row, 7 in the second. It is going to, I apologize, it's not 2-7, it's 2-5. So it wants to be like neon. It needs 3 electrons for happiness. So, and I have 2 nitrogens. So what nitrogen does is each nitrogen is going to share 3, and by doing that, it can get its full outer shell of 8 electrons. So I'm going to go X, 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 1, 2, 3, 4, and 5 for this nitrogen, and I'm going to go dot, 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 1, 2, 3, 4, 5 for this nitrogen. And then if I just confirm my choice, so left-hand nitrogen has 1, 2, 3, 4, 5, 6, 7, 8 electrons. Right-hand nitrogen has 1, 2, 3, 4, 5, 6, 7, 8 nitrogens. Happiness is nitrogen now. So an N-N-N bond are 3 shared pairs of electrons. And 1 sigma, and you will only ever have 1 sigma, and the second and third shared pair are called 2 pi bonds. Now we have done a good chunk of stuff. There is a QR code for dot and cross. In your class notebook there is a page or a list of questions in the class notebook that you're going to try. Before you do those, I'm just going to talk about boron, because boron is a weird one, as is beryllium when we get to it. So you should have space on page 144 to just talk about these. So if you look at boron, boron has 5 electrons and they're going to be distributed as a 2 and a 3. So boron is a bit weird in that it is not going to reach this 8 electrons. So if boron has 3, boron only wants another 3 in it for happiness. So 3 electrons for happiness. So boron is weird. It will only have 6 electrons in its outer shell. So there is a caveat there. It doesn't quite reach this noble gas structure, so it won't ever be for full outer shell or full outer energy level. And